Hi, I'd like to use the video to elaborate the concept of doing continuous time convolution graphically. First, say we just trying to recall if we are going to do the convolution between x of t and h of t, then analytically the y of t will be equal to integration from minus infinity to positive infinity. Then we change into x of tau, then it become ht minus tau d tau. Right. Important thing is, like to remind you that the variable is no longer t. The variable in the convolution becomes the tau. Right. The reason why, because we like to work out how yt is at different t. Now, so maybe the interesting thing about this, so what this actually means, ht minus tau, it means this function is going to flip to the other side, to flip to the left-hand side. If the function h of t is something like that, then if this is h of t, then h minus t simply become flipping it to the other side. But suppose if h of t, this is h of t, then h minus t will become something like that. We just flip it to the left hand side. Okay, so this is what ht minus tau is about. Now maybe we can use another waveform to show you. Suppose if we are going to integrate, right, two function minus infinity, positive infinity, rect, this one, tau minus 1. This is a rectangular function. I explain it to you what rectangular function later on. Rect, this t minus tau over 2, d tau. So we are actually trying to find the convolution between t minus 1 convolved with rect t over half. So the interesting thing is this one and this one. So this thing will become t minus 1 will become something here, and this thing, right, this is a function of, assume this is the function of rect t minus tau, then you flip it. That means they are exactly the same along this axis. Now, I'm coming back. So what does it mean from minus infinity to positive infinity? Minus infinity to positive infinity, that means we are going to move this particular function from minus infinity all the way slowly to positive infinity, this minus infinity. But at the same time, this x tau is still staying somewhere over here. Okay, so one function doesn't move around, this function doesn't move around, and another function just move from minus infinity gradually to positive infinity. So the integration side, it means try to find the area overlapping between them. This is what the whole integration is about. Now, I'm going to use the next example to further elaborate the whole mechanism of it. Because sometimes it is quite difficult to use analytical method to solve the integration. Now, take for this particular example, we like to find the convolution of, red t minus 1 convolve with red t over 2. Now, basically, what is a rectangular function? I like to talk about a rectangular function is in such a way. So I start from minus half to positive half, and then go to 1. So the whole area is equal to 1. So basically, it is a kind of rectangular function. So when we are actually trying to find the convolution of these two, so first we like to draw the waveform. The waveform is quite simple. Right, the waveform, as I said, this is a rectangular function. Then for rectangular function, t over half, that means we are going to expand the function in this way. So we are going to have 1 and 1 here. So we've got rectangular t over 2 here. So for another function, red t minus 1 is also very simple. We simply trying to shift the function. So we shift the function from here to there. So we've got something like that by shifted by 1 here. So basically, we've got a rectangular function by shifting the y-axis into the left-hand side. So we have this one is red t minus 1. So after we have got the two waveform here, then we are going to do the second step. The second step of that is trying to flip it. We flipped either this one or either this one along the y-axis. But in this case, I would like to choose flipping this one into the y-axis. Why I like to choose flipping that in the y-axis? Basically simple, because you flip it along the y-axis, so the waveform becomes exactly the same. It doesn't change. But if you're going to flip this one, the waveform will turn out into something like that. Either thing with light the same. Now, so in this case, I like to start from flipping this one. Once when I flip it, then we start to do the interesting job. The interesting job is try to start to move this one. Originally, we noticed that it was here. Originally, it was here. Then we shift the waveform of this waveform from far left. From far left. This is what far left is about. But once when we shift it to far left here, there's no overlapping between this waveform and this waveform, so it doesn't matter. So we start to shift from far left all the way from where to here. Okay, once when we shift waveform from far left all the way to here, that means it starts the overlapping. It starts the overlapping. That means when we shift the waveform by minus half, it it was there, but when we shift it by minus half, then the waveform becomes here. So it starts to have a little bit of overlapping. Then when t is equal to 0, okay, that means there's no shifting, is here. Then this is the overlap with this waveform. So what we can see is when t is half, t is equal to minus half, it starts to have overlapping. When t is maybe minus 3/4, it might be there, more overlapping. Then when t is 0, you have more overlapping. When t become half, then what you can see is when t become half, then you see this is overlapping. So when t is half, we start to have maximum overlap. So when t move further, t is equal to 3/2, okay, somewhere here, so we still have the maximum overlap, but what we can see, the waveform starts to become there. When t become 2, okay, then the overlapping become less. When t become 5/2, there is 3/2, there is here, so there is no overlap. So what we can see is we start to have overlap when t is equal to half, start overlap. So when t is equal to, so we have a little bit area. So when t is equal to maximum overlap, when t is equal to 3/2, we also have maximum overlap, but what we can see, the waveform starts to move there. So when t is equal to 2, so we don't have any more overlap. So when t, that is what it is about. So the next step is what we are going to work out the overlapping area. So this is the overlapping area. When t is equal to here, maximum overlap. When it is maximum overlap, so we have an area. This is 1 times the magnitude. So 1 times 1 is equal to 1. So the area is equal to 1. Okay, so what we can see is when t is equal to half, it starts to have overlap. It linear increase until when t is equal to half, it becomes maximum. So there is half. So it maintains all the way to constant until t is equal to 3/2. Okay, so it starts to decrease until when t is equal to 5/2. Okay, so when t is bigger than 5/2, there's no overlap. So what we can see that a linear increase from minus half to half. Then 1 is the area. It starts to decrease linear. So here, so what we can see, the waveform is something like that. Okay, 5/2. Okay, 3/2. Okay, this is half. This is minus half. So this is the waveform of a convolution of this particular function using graphical method. It is easy, and what you need to do is just to do it step by step.